Hey, this is Leach with Simpson Math, and in this video, I want to give just a brief introduction to confidence intervals for a population proportion or a one proportion confidence interval. I just want to talk a little bit about the math behind it, what's a little bit different from just our general introduction that we had. Then I'll show you how then we can also use the normal model to approximate this proportion situation. All right, so let's get started just with this little overview. So I want to talk about just our general structure of our confidence intervals. So they are made up of a point estimate, which we know is wrong, but is our best guess. But we can be more correct, we can be more accurate, we can basically be right more often if we can fatten up that interval, fatten up that estimate from a single number to an interval with some sort of margin of error. So at a certain point, and then we're going to plus and minus on either side of it, so we can kind of thicken it up. We'll basically be right more often. So generally, our point estimate is a sample statistic. Next section, it'll be our sample mean. In our introductory section, it was we were talking about the sample mean as well. But specifically, this time we're going to be talking about our sample proportion, which we'll talk about is called p hat. Then we have our margin of error as made up of two parts. We have our critical value and our standard error. In general, remember when we first learned about the empirical rule, I always said that it was if I go up 2 standard deviations, down 2 standard deviations, that's approximately 95% of the data. We're basically sticking with that idea. About 95% of the time, I would like to try to produce an interval that captures the truth. I mean, ideally, we would try to do all of it, but then my interval would be so wide it would basically be useless. And so that's where we shoot for the about that 95% mark for default. And recall that we said that there was about 2 standard deviations as an estimate back when we talked about the empirical rule. Well, we're going to be a little bit more specific, and it's not going to be 2. And then we can also kind of treat this as a little bit of a dial, because maybe I don't want to be 95%. Maybe I only want to be 90%, or maybe I want to up it to 99%. And so this is the dial or the knob that we'll use to control that. And then we have our standard error, which in this case is this formula, which I'll talk about in a second. So let's talk about this sample proportion. So in general, all throughout this course, when we've talked about a proportion, it's our number of successes over our sample size. So our sample proportion, our observed number of successes, or sorry, our observed proportion of successes. We could call this just like a little baby formula for it would be x over n, where x is my number of successes and n is my sample size. And we read this as p hat. I should write that down. This symbol, I don't remember if we've seen it or not this in this online course, if you're in my online set course. In my face-to-face stat course, we've been talking about p hat for ages. But if I had to write it like out in words, I would call it p hat, p hyphen hat. So we just read that p hat, so it's p with a little hat on it. And that hat is signifying that it's the sample proportion as opposed to what we're trying to estimate. When we're trying to estimate the population proportion, that is just regular old p. Now, if you're looking around at other videos other than me, I mean, why would you? But I mean, if you did, sometimes they might use pi instead of p to represent the population parameter. An applet that I'll be talking about later uses pi, but kind of default instead of p. But so it's kind of accepted thing. Most education things we use p because I use pi, that kind of freaks you out from your geometry days about it being about 3.1 for the ratio of the circumference over the diameter. We don't stress people out with that. So we typically just do with it being p for our population proportion. So, but if there's a hat on it, it's the sample proportion. So just a reminder also, when we talked about the binomial distribution, we saw that Q was our proportion of failure. So Q hat would be our sample proportion of failure, or 1 minus p hat. Now recall that in the binomial distribution, when we saw that back in the day, the binomial distribution, that was our number of successes. That's cool and all, but we're typically more interested in our proportion of successes when we estimate that proportion instead of the number, which is also helpful because then it's more relative. If you heard that 60% a proportion of 0.6 of a certain population is supporting political candidate A, well, that's telling me that proportion, I don't have to worry about, well, out of how many people. If you heard that 500 people support political candidate A, you're like, cool, out of how many? You're going to have to ask that question. So if I give it to you as a proportion, then we don't have to worry about the out of how many, then it's automatically kind of relative there. So that's why it's a little bit more useful and we like it. So, but that's important that we've studied this. We've studied the binomial, which is our number of successes. Um, and we're going to be turning this into our proportion of successes. And we do that, notice, by just dividing by n. This x is basically our number of successes. And so we'll be dividing this by n to produce the proportion. Just a little bit of a caveat. If you took this formula and solved for x, you would get x equals n times p hat. So it means if I take n and p hat, multiply them together, that gives me my number of observed successes. If you put yourself back into when we talked about the binomial distribution, n times p should be something that was familiar, and that was the mean of the binomial distribution. So that's not a coincidence that's how that lines up. And if I needed to know my number of failures, it would be n times q hat. All right, then just a reminder that our critical value is the same stuff that we talked about back in, like, if you're in my online course 6.1. So our book uses Z sub C. I personally would often use Z star, same difference. Remember, for example, something like if I was wanting to be 95% confident, my ZC would be 1.96. Notice how that's almost 2. It literally rounds to 2. But from our if I was wanting to be 90% confident, then I would need to lessen that back, turn that knob down just a little bit to be 1.645. So I would only go up 1.645 standard deviations and down 1.65 standard deviations from my statistic to try to capture the truth. Last time we talk a little bit about this math, and then we'll get into how we can approximate this using the normal distribution. So if you recall from the binomial distribution, we have this was the formula for the standard deviation, the square root of npq, where q is 1 minus p. And recall that binomial distribution was our number of successes. Well, I don't want just the number of successes now, I want the proportion of successes. So if I was to be talking about the sampling distribution of a sample proportion, so we've talked about the sampling distribution of means, and this follows suit in an interesting way. Whereas imagine a distribution that only had a pile of zeros and a pile of ones. So data values just at 0 and just at 1. If they were equal, then it would be a 50% or 0.5. If my ones were bigger than the 0, then it would be like something like 0.6, 0.7, 0.8, 0.9. If my zeros were bigger, that would be something less than the half. So if I have that distribution, the central limit theorem says that if my sample size is large enough, it doesn't matter what that starting distribution looks like, even though they're just two little towers. If my sample size is sufficiently large, then the resulting shape of that sampling distribution is going to be approximately normal, and that is also going to be the case with this proportion situation. But we had a formula for the means, and that's sigma over square root of n, which is basically that same thing. Sigma divided by sigma over this n-ish. It's kind of the same idea, but what we're doing is we're turning this into a proportion a little bit. Actually, take it back. Sorry, rambling. If I was going to edit this video, I'd get this part out because I just started rambling about something. But okay, so what we're going to do though is we're going to take this instead of using the sigma over square root of n part, which this is kind of related to that, it's kind of similar. We have a specific formula that we already know precisely for that binomial distribution. And since we're wanting to have the proportion, for this, I'm just going to divide by n. So notice if I do that, my basically x divided by n, this would now be my the standard deviation of my sample proportions. So let's talk a little bit about the math as to how this shows. This is, when I teach this in class, it's like, this is for those of you who are a little bit more mathy inclined and you kind of like to connect the dots. I'm someone who I like to know, well, why is it like that? Because then I understand it and I can learn it. And if I need to memorize it, I can memorize it better. So that's what this is for. So if I divide by my sample size, divide by n, I'm turning it in from my x divided by n. So I'm now basically dealing with proportions. So that's the logic behind the divide by n. So now I'm just wanting to simplify this. And I know for the super mathy people, I'm kind of unrationalizing. I'm making this be a square root, but I'm basically making the formula be easier instead of having two different n's. So do you agree with this statement that I could write n as the square root of n squared. Those would equal each other. And n is a positive number, so I'm not having to worry about any weird plus or minus things because n is the number of things in my sample. So my sample size, which will be positive, so we don't have to worry about that. So if I could replace n with the square root of n squared, we can use our properties of square roots to put this all under one big square root. So now I have npq over n. So I have an n on top and two n's on bottom, so I can reduce the n on top with one of the n's on bottom, pardon me, and be left with just the square root of pq over n. In terms of just p, it would be p times 1 minus p over n. So that should be a familiar way of being able to, that's a little bit, sorry, not, it's using this binomial formula, but more importantly, this formula down here is a little bit nicer and cleaner than dealing with this one, and you'll see one of these in the textbook. Now, that's the standard deviation of the sample proportion. What about the standard error? So if I don't know what p actually is, I'm using p hat, so the center of my distribution would be that p hat. So the standard error, which is basically the same thing, notice it's using the hats instead of the p's. So that's why in our formula here, we have our hats in that process. So there is a little bit of a condition behind us being able to use this. And that has to be, I forgot to write it down ahead of time, but that has to be, let's do this blue, when in p hat or, sorry, not or, and in q hat, they both have to be greater than or equal to 5. This is what our Larson textbook says. So if you're in my online stat class, and at the time of this recording, we're using this book, even though I hate it. Hate this book. And this is one of the reasons I'm not a fan of the 5. I have lots of reasons I don't like this book, and this is one of them. I don't like the 5 personally. I would use this. I would use the in p hat and in q hat would have to be greater than or equal to 10. That's the kind of more standard approach. In my face-to-face class, this is where I use at least 10, and I'll talk about why that is in a second. But if you're in my online class and we're still using Larson, then we can get away with just 5, according to that book, even though I kind of disagree. So let's take a look at the logic behind this. Oh, real fast, one more thing. Remember, this NP hat, we talked about that just a second ago. This is my number of successes. And this NQ hat is my number of failures. And this is an and situation. Okay, both of these have to be true. Okay, they both have to be true in order for me to be able to use the normal distribution to talk about this. So the reason why what's nice about knowing that this is the number of successes, sometimes these problems we're going to hand you. I'll say, oh, a sample of 1,000 people took the survey and 600 of them said yes. Well, 600 of them would be, the 600 people who said yes would be basically X or in p hat. I don't have to do any math to find that number when that's handed to me on a silver platter like that. Likewise, I could ask a question. I took a sample of 1,000 people and 60% of them said yes. Oh, well, if I need to know how many of them said yes to know if it's more than 5, then I would do 1,000 times 0.6 and get the 600 and be like, oh yeah, that's more than 5. So they both, if you think about this logically, they both have to be bigger than 5. So I really only have to check the smaller of these two numbers to be able to see if it's bigger than 5. But of course, if MyLab for some reason asks you to check and enter those numbers, then you should you have to find them both. All right, so let's take a look at just a little bit of an explanation about the relationship between the binomial distribution and this normal distribution and how we can approximate the two. So what I have here programmed in here, this is just a demonstration. This is not a thing that I'm expecting you, the student, to do. I have a little slider for representing n, a sample size. A little slider here representing p, my population proportion, the proportion of people who would say yes, my proportion of successes. And I have two pictures. The orange is a normal distribution, a smooth curve normal distribution. Oops, let me just show that one. Smooth curve normal distribution. that has a mean and a standard deviation, and the mean and standard deviation I'm using is n times p is the mean, and square root of npq for the standard deviation, which is what we just said the binomial distribution mean and standard deviation are. So if you look at the binomial distribution, that's the blue sticks, remember that this is a discrete situation. There's a section in the book, if you're in my online class, if you look at 5.5 in the book, I skipped that section as a question with homeworks and stuff you see on the test. But if you look at that book, so because it gets too in the weeds, it becomes a whole thing. But do you see how this is a discrete thing? I can't have 24.2 successes. I can have 24 successes, 25 successes, but I can't get a decimal in between. So we're approximating this discrete situation with this smooth curve normal situation. That's neat. Well, and if you look at the tips of these blue dots, they match up pretty well with this normal curve. And as long as what I have here, if this n times p is at least 5, according to the Larson book, I would say 10, and most other stat educators would say 10, or nq, if both of these numbers are bigger than 10, then we're good to go, or bigger than 5 for Larson, then we're good to go. So this matches and lines up pretty well to approximate the normal distribution to the binomial distribution. But we're not doing the binomial distribution. We're doing proportion. So basically, if I take this situation and divide by n, so it's my x divided by n. So now it's proportions. Let me make sure I'm zoomed in on my, I'm zoomed in on my normal as best I can. I'm going to zoom in on the normal with the proportions, and this curve is basically going to be in about the same spot. But now I'm down between, look at my x-axis here. I'm now down at these proportions between 0 and 1. So my number here, this is my number of successes between, my sample size is 40. So basically between 0 and 40 versus my proportions here, which is between 0 and 1. So if I was to zoom out to between 0 and 40, here, see how these blue dots? This is the 0 to 40. If I come over here to my proportions, and I look at between 0 and 1, it's in that about same spot, about that same height. So this is what we're doing the math with at this point. So that's that main difference. It's just a divide by n. So let's talk a little bit more about that. I can't as cleanly show you the proportions with the divide by n, but so imagine that all these were my proportions instead of my number of successes. So if my sample size is a little bit too small, so let's say like the sample size is 6, and I try to zoom into the normal distribution. Let me turn off this red one. Do you see that this normal distribution, do you see how much space there are between all these blue things? We're not going to get super great estimates when it's super kind of discrete like this with a really small sample size. So that's kind of problem number one. Another problem with this with a really small sample, so if it's a really small sample size, it's too discrete, too much kind of daylight in between these to try to be approximating that. Another potential problem is, especially if I have a small sample size and my proportion is really low. So looking at this, look how much area is less than 0. I can't have less than 0. Let me actually look and see what is less than 0. In this case, 21% of this distribution is less than 0 in an impossible area. So that's not a good idea. So if my p was 0.1, what's the smallest sample size that I could get away with? So that way it's satisfied where n times p or n times q is 1. We'll take a look at this m, and I'm going to slide this n up here. Let's see when this reaches 5, at least 5. Scooching up, scooching up. I'm at 3, 4, 5. So notice 50 times 0.1 is 5. So according to the Larson situation, our textbook, that if I want a sample size, if I have a sample size of, sorry, rewind, if my p is 0.1, the smallest sample size I could get away with is 50. I'm still not a fan of that because there's still like almost a whole percent of chance that it could land in this impossible territory. That's why I actually would like it to be closer to 100. That would be in P and Q would be at least 10. And then the likelihood that he lands something down here is more than 3 standard deviations away. So that's, that's why we like that. Plus also, look how much denser these blue bars are than than when it was just 5. Right here, look how the amount of space between, basically amount of daylight kind of between here. I only have like basically 12 possible successes that could land under the normal curve, versus here we have about 20 possible successes that could land under the normal curve, which is a little bit more denser since I'm trying to approximate a continuous distribution with a normal one. Let me back up again to the binomial, this full space, and remember that if I have uh, if my p is really, really small, I would have to have a really large sample size to be able to compensate it. Or if my p is on the other end, if my p is really, really big, that same thing would happen. But if my p is like 0.5, if my p is 0.5, I could get away with a sample size of 10. Do you see that? If my sample size is 10, according to Larson, if my p is 0.5, I could have a sample size of 10. Again, I'm not a fan of that. I would want at least 20, and it would kind of match and line up a little bit better. All right. I think I'm kind of done, but I'm going to ramble for just a second. I'm going to show you a different applet, just to kind of show you about how this standard deviation formula does work. So give me 1 second. I'm going to push some buttons, change my things around, my presentation around. All right, push this back. Okay, so what I have here, just have Desmos because I want to do a little bit of math. And this is another applet that in my face-to-face class, I use this one a lot. But what I have this one is I have a proportion set right here. This proportion says 0.5, so this is the population proportion. If I do a sample size 10, I'm going to have this thing just generate a bunch of samples. So, oof, my head's in the way. Well, this x-axis is 0.5, so this is like 0.1, 0.2, 0.3, 0.4. Sorry, my picture's in the way. So if I say, hey, applet, give me pull, basically it's like flip a coin 10 times and tell me how many heads you got. They flipped a coin 10 times, it counted 6 heads, so it graphed a little dot at 0.6 right here. Do it again. Well, it did it, flipped a coin 10 times and got 7 heads. Do it again. Flip a coin 10 times and I got 3 heads, and it put it right here. So do that over and over and over again, and you see how we're getting more and more dots. So I'm simulating a sampling distribution where each of these dots is representing a p hat. And I'm going to try to see and develop a trend. I'm going to speed this up instead of just 1 at a time. Here's 10 at a time, watching it grow. Here's 100 times. Let's throw in like 1,000. So here I've done it about, where does it say, about 2,600 times. And we can see that it's this kind of symmetric look. It's according to Larson, this is approximately normal enough that we could use the normal distribution. I would want it to be at least twice as big. I'll show you what that looks like in a second. But here my standard error is 0.158. That might be a little bit small, but this is 0.158. I want to use our formula for the standard error formula. So I'm going to do the square root of p hat cube hat over n. So 0.5, I'm going to go ahead and get my fraction in there. 0.5 times 0.5 over n. And when I do, I get 0.158 with more decimal places. So it's interesting that this distribution on this left was created just by random luck. I was just said, hey, computer, give me some random dots. And following this pattern, it gave me these random dots. And oh, look what happened. I got the standard deviation, or the standard error of this distribution was 0.158. That's interesting that it follows that formula. Let's increase my sample size to 20. Oof, it got a little slow. There we go. I probably have too many things running on my computer. All right, so I can do the same thing. Now I'm going to say, hey, computer, flip a coin 20 times and tell me how many heads you get. It flipped it 60 times, 50 times. I can't speak. Flip a coin 20 times and it got 10 heads, so 0.5. Do that again. It flipped it 20 times and got 9 heads. I flipped it 20 times and got 11 heads. Do that a whole bunch of times. And when it does, it ends up getting a distribution that looks like this. Well, let's see what happens if I increase my sample size. I'm just going to copy and paste. If I increase my sample size to 20. Notice that the sample size got smaller. This is consistent also with what we with what we studied in I think 5.4. When we increase our sample size, the variability decreases, which should make sense. If I flip a coin 5 times, let me do this 5. Let me go to the other end. If I flip a coin just 5 times, and I was like, if you're like, OMG, I just saw my stat teacher flip a coin 5 times and get 4 heads. I can't believe it. There's an 80% chance that that happens. Like, so not 80%. There's a point 0.8. He got 80% heads. That's astounding. No, that's not very astounding. Let's see how often we can get at point 0.8. Well, the first few I got 3.2s in a row, which is about the same likelihood. Um, so if I do this, we'll see that the likelihood that I get point 0.8 happens quite a lot, right? Look at the standard deviation for this. If I do it just 5, that's 0.22. So notice that how as we increase our sample size, the sampling distribution is going to get smaller. We can see this numerically here, and just think about it. If I flip a coin 5 times and get 80% heads, that's not very surprising. It happens all the time. According to this simulation, if I said 0.8, that happens about 21% of the time. All right, then let me do. But if I up it to like a sample size of 50, so I said, "Hey computer, flip a coin 50 times." It says, "Okay," and it did, and it got 23 heads. Do that a whole bunch of times. Um, so it did, and let's see what I get when I do that. So here I get sample size. So I sample size 50. So then my standard error here is 0.07, which 0.070, which lines up with my standard error here. And the likelihood of getting an 80 doesn't even happen. Out of the 2,000 times of doing it, I didn't even get it once. So remember, as our sample size increases, the likelihood of getting those really weird numbers decreases, and this gets smaller and smaller and smaller and smaller. That's why our standard error gets smaller. So hopefully, seeing this graph helps. In my video that you should watch next, it's next on my lab. I go through 2 different examples, and I use then the Rossmann-Chance applet. At the end of the day, guys, you're not gonna need to be doing this math because you're gonna be able to have technology to help you out. But it's really important. In my opinion, it's helpful for you to know what's happening behind the scenes, so that way you can better understand it. Okay, I think that's it. So I hope this video helped. I will see y'all later, and I'll see you in the next one. Bye.